Thermodynamics will be discussing the second and third laws of thermodynamics, specifically dealing with entropy and free energy. When we talk about these concepts, really what we're discussing is spontaneous processes. Will a reaction occur on its own or not? Spontaneous has nothing to do with time. So a spontaneous reaction may be fast or it may be very, very slow, but that's irrelevant. Will the reaction occur on its own by itself with or without help? Now, generally speaking, spontaneous reactions, if it's spontaneous in one direction, it's non-spontaneous in the other, and temperature does play a role. You may have a spontaneous reaction at one temperature and not at another temperature. The last thing to consider are reversible and irreversible processes. So in reversible reactions, again, it goes back to that very first idea. If I'm spontaneous in one direction, I'm non-spontaneous in the other. So reversible systems, though, the biggest difference between reversible and non-reversible is that I can reset the system. By adding energy or putting energy back in, I can reset it back to how it started, and then it can spontaneously do it again. It's sort of like climbing a slide. I can climb to the top of the ladder of the slide and slide down, go back up, climb back to the top, and reset, so to speak. Irreversible, you can't do that. If a reaction is spontaneous, you can't go back. It's sort of like the breaking of the eggs in the first example. Now, this brings us to entropy. Entropy is, in essence, the randomness of a system. That's the main thing. You also often hear it called, the chaos of the system. In essence, it has to do with the motion of the particles and how the particles can move. Notice that entropy is a state function, meaning all we have to care about is final minus initial, and we would set it up exactly the same way we did enthalpy, meaning it's basically products minus reactants. So I take my total entropy of my reactants, total entropy of my products, and that's where I get my total change in entropy. Now, this is related to the second law of thermodynamics, which basically says that the entropy of the universe is increasing, and this is because of spontaneous processes, irreversible spontaneous processes. The point being that we see no change in a reversible process, but irreversible processes, the change in entropy is always greater. This is why the entropy of the universe is always increasing. Now, the way we look at entropy is both on the molecular scale, we'll look at it in terms of physical properties, etc. The main point here is that this is what's known as microstates. Basically, all that means is that there are multiple ways a particle can exist. So I can see changes to the lengths of the bonds, the position of the bonds. I can see rotation of the particles. Ultimately, the different ways that I can rotate, switch, and modify a particular, sorry, you can see where I'm at, mainly is if I can modify the positioning of everything, that counts as a microstate. So in essence, larger molecules will have more microstates than smaller molecules, and the more microstates I have, the more entropy I have in a system, period. It's that simple. Don't overthink it. This means that temperature, volume, and the number of independently moving molecules impacts the microstates. It impacts the entropy. And that's the main thing here, because really, ultimately, it's these things that we care about in terms of impacting entropy. And we see this carried out in our physical states, so that the entropy of a gas is greater than the entropy of a solid. You also see it when we talk about solutions or solvation, because generally speaking, notice the generally, there are always exceptions, but generally speaking, whenever you put a solid and it's solvated, it becomes dissolved, you have more entropy than you started with. The last thing to recognize is generally the more gases I have, the more entropy I have. The fewer gases, the fewer entropy. If I go from a liquid to a gas, I increase entropy. If I go from a liquid to a solid, I decrease entropy. So you kind of get the idea. And this is in essence the third law of thermodynamics, that when I hit absolute zero, there is no entropy in the universe. That is in essence the third law. Now, standard enthalpies are calculated in very much the same way that we saw with heats of formation. You have a chart, it's going to have a table with all these standard molar enthalpies. The main thing I want to point out here is the difference in unit. When you look at entropy, notice it's joules per mole Kelvin, not kilojoules. So entropy is a factor smaller in terms of the role of energy. So the reason we really care about entropy in the universe, is this idea of Gibbs free energy. Basically, when we talk about Gibbs free energy is the energy in the surroundings, in the universe, that is available for a particular reaction to become spontaneous. Okay, so notice a couple of things here. If my delta G is negative, I have a spontaneous reaction. If delta G is positive, my reaction is not spontaneous, but it could be spontaneous in the opposite direction. If delta G is 0, this is equilibrium. This is something we'll focus on later on. Right now, the main thing you have to know is negative, spontaneous, positive, not spontaneous, but potentially spontaneous in the reverse direction. So Gibbs free energy being a state function like entropy and energy and enthalpy, I can always go back and look at it in terms of products minus reactants. Remember, anytime we have a delta, anything, it's always final minus initial. Products are always final, reactants are always initial. Now, where we see the interaction of these three components, the free energy equation is, in essence, delta G equals, looks like a 6, but it's a G, equals delta H minus T delta S. So the importance of this is that temperature can impact certain aspects of free energy because, as we saw earlier, temperature can impact entropy. Well, when we look at this, we end up with various outcomes, various expectations. So if my delta H is negative and my delta S is positive, well, I'm going to have all negative numbers, so my delta G is ultimately going to be negative. That's what they're showing you on this first line. So you want to be so familiar with this table that you can see it in your sleep, which I know makes you all very happy. The other thing is, notice, if my delta H is positive and my delta S is negative, well, then my delta G becomes positive. That's this situation. I have something that's not spontaneous. Oops, this one right here, sorry. Okay, so if I'm not spontaneous, that means that I'm potentially spontaneous in the reverse direction, and or I have to add energy or give it some, there's not enough energy around it to get in. These last two situations are what are really important because they are where we see the temperature dependence of Gibbs free energy. I can have positive or negative when I have these situations strictly dependent upon temperature. So I can see the impact of high and low temperatures on my Gibbs free energy.